Today we're looking at the Chapter 12 AP Chemistry packet. We're going to be talking about chemical kinetics. And chemical kinetics again answers the question how fast a reaction occurs. And this question can only be answered by experiment. You can only figure this out by doing experiments to know how fast a reaction proceeds. So let's take a look at a reaction where we have 2A plus B yields 2C. We're going to start looking at the concentration of A over time. So you could see that over time, 0 to 10 to 20 to 30 to 40 seconds, let's say, the concentration of A is decreasing. It makes sense that the concentration of B is also decreasing. And it makes sense that the concentration of C is increasing because we are forming C. So what you're going to want to do is you want to graph this. So we're going to graph this information. We'll make this a little smaller so we could fit it all on the paper here. And we're going to take a look at, first of all, A. So A is going to be starting at number 1 molarity, 1 molar. So we're going to write this over here. And then at 10 seconds, it's going to be 0.5. So we're going to put a 0.5 right over here at 10. And then we're going to have a 0.25 at 20. And at 30, we're going to have a 0.125. And lastly, we're going to have a 0.0625 at 40 seconds. So if you wanted to attach these smooth curve of best fit, you would see that this roughly goes like that. Okay, let's take a look at letter B and see what's happening with the B. The B started off also at 1 molar, so I'm going to put another dot right there. But after 10 seconds, the B went down to 0.75. So here's the B at 0.75. And then now we're going to do the 0.625 at 20 seconds, which is going to be about here. And then the next one is at 30 seconds. It's going to be at 0.55, which is going to be about here. And then the next one is going to be at 0.051, which is roughly right here. So when you attach these, you'll see that the B curve looks a little different than the A curve. And that should make sense to you because if you look at the coefficients, the A has a 2, whereas the B has a 1. So the A is going to decrease at a faster rate, specifically decrease twice as fast as the B will decrease. And by the same argument, when we look at the C, we're going to notice that the C is going to increase at the same rate that the A decreased because they both have a coefficient of 2. So let's graph the letter C. And letter C is going to start off at 0 in the beginning. And then after 10 seconds, it's going to be at 0.5. That's also going to be the same dot right there. And then it's going to be at 0.75 at 20 seconds. So we're going to put a dot right here. And then it's going to be at 0.875 at 30 seconds, which is going to be about here. And the last one is going to be at this point right here at 40 seconds. And when you draw this one, you're going to see that it's pretty similar. Whoops. It's pretty similar to the A curve, except it's the opposite. Okay, so you can see here what's going on in terms of graphing the rate of change. Okay, so one more time, the A decreases at twice as fast as B, and the C increases at the same rate that the A decreases. All right, so now what we're going to do is we're going to look at the next page and see how to figure out average rate. Now because I'm not going to be able to turn pages very easily, I'm going to refer to the second page while staying on this page. So we're going to try to find in number 1 on the next page the average rate of consumption of A and B and the formation of C in the first 10 seconds. So in the first 10 seconds, A is going to go from 1 to 0.5. That's going to be the A. Whereas the B is going to go from 1 to 0.75. And the C is going to go from 0 to 0.5. So when we see those numbers, we're going to do them on the next page in a moment. But in order to understand even better graphically, we're going to use a ruler. So if you don't have a ruler, you might want to pause and come back when you're ready. If we graph the average of A decreasing, you're going to see that that line is going to go, sorry, this is the A's right over here. Let me erase that real quick. I'll just go here. So A is going to go on the blue decrease. It's going to have a slope of this in the black. Okay, whereas the B decreasing in the first 10 seconds is going to be this black line. And then the C increasing, when you draw that average for the first 10 seconds, is going to be this line right here. Kind of with the ruler. I tried. So you can see again the slope of the line for the blue. This slope right here for the blue is quite steep. It's going to be twice as steep in absolute value as this line for the red. And then the blue going up for the C is going to have the same slope, but positive, as the A did going down. So next we'll go to the next page and do all the math for finding out the actual numbers of these slopes. Let's say we wanted to get the average rate of consumption of A and B and the formation of C in the first 10 seconds of this experiment. The first thing we need to do is figure out what are the concentrations of A at the end minus the beginning. So A went from 1 to 0.5, so you always do the end minus the beginning. That's going to be the molarity over the change in time. The ending was 10 seconds and the beginning was 0 seconds. So you're going to have a difference of negative 0.5 molar per 10 seconds. And when you do the math for that, you're going to get negative 0.050 molarity per second. Let's try to neaten this up a little bit. So 0.050 molar per second. That's how much was used of the A on the average, just the average, in the first 10 seconds. Now if you're going to do letter B, you're going to take the ending concentration after 10 seconds, which was 0.75 molar. It started at 1 molar. And the change in time again was 10 seconds, so 10 minus 0 seconds. And when you do the math for that, you're going to get negative 0.25 molar per 10 seconds, which equals negative 0.025 molar per second as the rate of consumption of B in the first 10 seconds. Now if we contrast that with C, we're going to find that C is being formed. So the final concentration after 10 seconds was 0.5. C started at 0. That's the molarity change over the time change, which again was 10 seconds minus 0 seconds. So if you do the math for that, it's going to be very similar to the first one. It's going to be positive, though, 0.50 molar over 10 seconds. And that's going to equal positive, I'll emphasize that, the positive sign. And that's going to be the rate of formation of C. So what you could see is that A and C are the exact same numbers but opposite signs, because recall that the equation was 2A plus B yields 2C. So because A and C have the same coefficient, they have the same rate but opposite signs, whereas B, the coefficient is 1/2 of 2, which is 1, and so its rate was half of the A and the C. All right, let's suppose that you need to do the same thing but for the first 20 seconds. So without doing all of these, we're just going to contrast the A here, and let's write that one out. In the first 20 seconds, the A went from 1 to 0.25. So 0.25 minus 1 molar, and now that's going to be a total of 20 seconds, 20 minus 0 seconds. Do the math for that, you get negative 0.75 molar per 20 seconds. And that's going to equal negative 0.0375 molarity per second. That's going to be the average rate in the first 20. If you contrast that with the first 10, you're going to notice that this number in the first 10 is a larger in absolute value than the number in the first 20, which means the reaction is slowing down for the consumption of A. Now, without doing a whole lot of work, you could easily get the other numbers for this. So if you look at the C, it's going to be the exact same. So if you look at the C, it's going to be the exact same number as positive 0.0375 moles per liter per second. Hopefully that recorded me. And the B is going to be half of the A, which is negative 0.0183 moles per liter per second. Let's do one more example where we're going to go from now t equals 10 seconds to t equals 20 seconds. So it's not from the beginning, it's from a middle time to another middle time. Well, let's rewrite the equation briefly, and it's going to be 2a plus b yields 2c. And we're going to look at the concentrations of A at time equals 20 and time equals 10. Those concentrations are 0.5 and 0.25. So we're going to do a subtraction of the end minus the beginning. So it's going to be 0.25 molar minus 0.5 molar divided by the total time change, which is 20 seconds minus 10 seconds. And when you let's suppose we want to find the instantaneous rate. To do the instantaneous rate, we're going to need to look at the slope of the tangent. Slope of the tangent line. You would never have to really get a number for this, but you might have to show it on a graph. And that's going to be the slope of the tangent line at 10 seconds in this case. And that would give you the instantaneous rate of either of these, in this case A, B, or C.
Now we're on page 4 of the AP Chemistry Chapter 12 packet, and we're going to be talking about differential rate laws. This is what your worksheet for homework is going to be about. And we're going to find that the rate depends on concentration. So a little background here, this HB stands for hemoglobin. It's not actually an element, of course, hemoglobin, and this is carbon monoxide. You know that carbon monoxide is poisonous. It's poisonous because it replaces oxygen in your blood. If you were to draw the Lewis structure of oxygen, it looks like this. And interestingly, the Lewis structure of carbon monoxide is quite similar. And so structurally, for some reason, your blood will prefer to take carbon monoxide into itself than oxygen if you were to inhale both gases, which is why the carbon monoxide is poisonous, because it disallows the oxygen to come into your blood. Now, what we're going to do is we're going to do several experiments here, and we're going to call this experiment 1, 2, 3 over here. And we're going to notice experiments 4, 5, and 6 are missing some numbers. So we're going to first focus on the ones with all the numbers there. In experiments 1 and 2, the difference here is that we doubled the amount of hemoglobin, but we kept the same amount of carbon monoxide in concentration. And let's look at what happened to the rate. We doubled the concentration of the hemoglobin, so this was at time 2, and that also happened to double the rate. So the question is, HB, hemoglobin, to what power, a double to what power gives you a double? So the answer is 2 to the first gives you 2. So now we're going to write a 1 here for the exponent of the hemoglobin. Let me pause for a moment and write down what we're actually looking for here. Number 1, find the order with respect to each reactant and write the rate law for the reaction. A rate law is always going to be rates equals a constant, which you can find, times the concentration of each reactant, in this case hemoglobin, raised to a power, times the concentration of carbon monoxide raised to a power. We just found that the exponent of hemoglobin is 1 because, again, when we doubled the hemoglobin and kept the carbon monoxide the same, the rate doubled. So this was times 1, so we kept it the same, and we got the exponent for the hemoglobin. Now we need to get the exponent for the carbon monoxide. In this case, we need to change this carbon monoxide while keeping the hemoglobin the same. So since the hemoglobin was constant, we're good. And now this is a times 3. And we look at the rate over here. This actually happens to be a times 3 as well. And so we look for our exponent here. And the question is, a times 3, or a triple, to what power gives a triple? The answer is 1. So we're going to write first power for this as well. And now I have my rate law. The rate law is rate equals K times hemoglobin concentration to the first times CO, carbon monoxide, to the first. Now what I want to do is I want to figure out what are the value and the units of K.
The hemoglobin is in moles per liter. So in experiment 1, what we're going to do is we're going to write all the numbers that we know. We know that the concentration of the hemoglobin was 2.21. That's raised to the first. And we know that the concentration of the CO was 1.00, also raised to the first. We don't know the K, so we're going to look for that. And we know that the rate was 0.619. So when we do all the math for that, we're going to get a 0.280 for the number. But the question is, what are the units? So you'll see that the CO is here, the HB hemoglobin was there, the rate is here, and now we know the K, but we need the units. So how do we get the units? We have to use with the units we know to figure it out. So we know that hemoglobin is in moles per liter, raised to the first, and we know that CO is in moles per liter, raised to the first, and we know that the rate is in moles per liter per second. So you could see that you could easily divide out one of the moles per liter from this side and this side, and then you'd want to multiply by the reciprocal of liters per mole in order to get the right side with no units at all. So you can see that the left side units will tell you this needs to be liters per mole second. Let's figure out a shortcut to figure this out quickly. All you do is add up all these, so 1 plus 1 is 2. You take moles per liter and inverse it, so liters per mole. Raise each one of these to 1 less than the sum of these two. So 1 plus 1 is 2, so you subtract 1, that's 1. So liters over moles to the first, each one, and then seconds, the time unit always goes on the bottom. Lastly, you want to fill in the missing values. There are 2 ways to do it. One way is to just use the rate law that you just found, and one way is to do it mathematically. I'll show you the mathematical way first. So again, we know that rate equals K times concentration of HB raised to the first times concentration of carbon monoxide raised to the first. In the missing value of line 4, we're missing the rate. So that means we're going to plug in this for HB and this for CO. So go ahead and write that in. Actually, I'm going to do experiment 5. So experiment 5, we're going to have these two right here for experiment 5. So I'm going to put 3.36 for the hemoglobin raised to the first times 2.40 raised to the first, and the K we already found out was 0.280, and that's going to give us our rate, which is 2.26. That's going to be moles per liter per second. So this is going to be a 2.26. If you do the exact same thing for the last one, but solve for the hemoglobin, you're going to get a 4.46 when you do the rate law as well. Okay, so let's figure out another way to do the missing value for the rate, which is line 4. So when you do line 4, you could see something interesting. You could see that in line 4, from line 3, this stays the same. So this is a times 1. And then if you notice, this to this is a times 2. So remember that the exponent for this is first power. So you're going to say a double to the first is going to be a double. So this is going to double right here on the right side. This is going to be a times 2. So if you double that, you're going to get 7.42, and that would be the right answer. If you want to double check it, you could simply use the rate law again and put in the hemoglobin to the first times carbon monoxide to the first times the K we know, and you would also get 7.42 as your final answer.